Before we move into the next major topic, which is linear vector spaces and quantum mechanics, I would like to insert a short bridging discussion. Up to this point, we have already studied Hermitian operators through their eigenvalue problems. We have seen real eigenvalues, orthogonality, completeness, general states, continuous spectra, and the distinction between bound and unbound states. Now, before we abstract everything into vector space language, it is very useful to pause and examine several additional properties of operators themselves. In particular, we want to understand how operators combine when two observables can be simultaneously sharp, and how the uncertainty principle naturally emerges from operator algebra. So this short section serves as a conceptual bridge. It still belongs to operator mechanics, but it also prepares us for the more abstract formalism that comes next. Let's begin with the most basic algebraic properties of operators. In fact, we've already used some of these properties before, so maybe I should have introduced this part earlier in this chapter. Most of these properties are quite natural, but it is still important to state them explicitly. If A hat and B hat are operators acting on a function f, then their sum and difference are defined in the obvious way as shown here. So the new operator simply acts by combining the results of the two original operators. Next, the product of two operators means successive action as shown. So operator multiplication is not multiplication of numbers, it is composition of actions. First, B hat acts on the function f, then A hat acts on the result. We also say that two operators are equal if they produce the same result on every allowed function, as shown in this equation. So operator equality is not judged by appearance, but by action. Finally, the identity operator does nothing. So we have the expressions shown here, or I should say we have the equations shown here. The identity operator is denoted by I hat or simply 1 hat. It leaves every function unchanged. At this stage, we should think of operators very much like transformations, as we have mentioned earlier in this chapter. They take one function and produce another. Once we think in that way, all of the later algebra becomes much easier to understand. Now let's continue with a few more operator properties. First, operator multiplication is associative as shown in this equation. So if three operators act successively, it doesn't matter how we group them. However, operator multiplication is not commutative in general. For an arbitrary function f, applying B hat and then A hat to a function f gives a result different from applying A hat then B hat. This means that the order in which operators or measurements are applied to a function or state matters. And this is one of the most profound differences between ordinary numbers and quantum mechanical operators. For example, later we will see that the position operator and the momentum operator do not commute. That non-commutativity is directly related to the uncertainty principle. Next, we define powers of an operator in the natural way. The second power means applying the operator twice, as shown in this equation. On the right-hand side, we have A hat act on f, and then A hat acts on that result. And in general, the nth power of an operator A hat acting on f equals applying A hat to f inside out n times in total. So first apply A hat to f, then apply A hat to that result, and so on. Therefore, we further have the equation shown here. Applying an operator a hat, a total of m plus m times, is equivalent to applying it m times and then applying it another n times. This is the operator equivalent of the exponent rule. Finally, the exponential of an operator is defined by a power series as shown in this equation. At first glance, this may look formal, but it is actually extremely important in quantum mechanics. For example, time evolution is expressed through an operator exponential involving the Hamiltonian. So even though this seems like a mathematical definition now, it will become physically meaningful in the future. Next, let's discuss the inverse operator. The idea is very similar to the inverse of an ordinary function. If G equals a hat acting on F, then the inverse operator, a hat inverse, is defined so that we can recover F from G as shown in this equation. If such an inverse exists, then applying the inverse of a hat after a hat returns the original function F as shown. So the inverse of operator A multiplied by the operator A equals the identity operator. Similarly, applying a hat after a hat inverse also returns the original input, the function G. So we also have the operator A multiplied by the inverse of the operator equals the identity operator. But here I want to stress an important point. Not every operator has an inverse. The inverse exists only if the original operation can be uniquely undone on the relevant domain. If different wave functions, or more formally, the vectors in Hilbert space, are mapped to the same result, then an inverse cannot be defined uniquely. This means that if a hat acting on psi 1 equals a hat, the same operator acting on psi 2, for psi 1 not equal to psi 2, then we cannot uniquely recover the original state from a hat acting on psi itself. This point may seem minor now, but later in physics and mathematics it becomes essential. Many operators have restricted domains, non-trivial kernels, or singular behavior, so one must always be careful when speaking about inverses.